Today, we are going to look at trigonometric ratios of specific angles. In the last class, we looked at the different trigonometric ratios called sin theta, cos theta, tan theta, cosecant theta, secant theta, and cot theta. Now let us find the values of these ratios for specific angles such as 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Let us park this table and figure these out one by one. Let us take a right triangle ABC, right angled at B. Let angle C be theta. Now, if angle C is theta, then the side opposite theta would be called the perpendicular or small p. The side adjacent to theta would be called the base or small b. Let us call the hypotenuse as small h. Now let us look at the first angle, 0 degrees. Now for theta to be 0 degrees, the vertex A would have to come close to vertex B. Or the vertex A would have to overlap with vertex B. Now let us get theta very close to 0 and identify the values of P, B and H. We can see from the figure that as A approaches B, my perpendicular would be reduced to 0 and my base becomes equal to my hypotenuse. So we know that sin theta is equal to P by H. Since P equals 0, sin theta becomes 0. Cos theta is equal to B by H. Since B and H are equal, cos theta becomes equal to 1. Tan theta is the ratio of sin theta by cos theta or P by B. We can see that the numerator is 0, hence tan theta becomes 0. Cosecant theta is the reciprocal of sin theta, which means that the denominator would become 0. And such a number cannot be defined, so let us call it ND, not defined. Secant theta would be the reciprocal of cos theta or h upon b, which would be equal to 1. And cot theta would be the reciprocal of tan theta or b upon p. Once again, the denominator is 0, hence the fraction cannot be defined. So now we have all the trigonometric ratios for theta equals 0 degrees. Now let us go back to triangle ABC, right angled at B, with angle C equals theta. Our definitions of P, B and H remain the same. This time we are going to squeeze the triangle such that C approaches B. Now my angle theta is going to near 90 degrees. In this case, my base is reduced to 0 and my perpendicular becomes equal to my hypotenuse. Once again, such a triangle is fictitious because with theta equals 90, my AB would coincide with AC and the triangle won't exist. But let us take theta very close to 90 degrees and figure out our trigonometric ratios. So similar to the column for 0 degrees, let us fill the column for 90 degrees. So I get sin theta equals 1, cos theta 0 and so on. Please note that the sin and cos value for 0 degrees and 90 degrees are interchanged. This would come handy later. Alright, let us go back to a triangle ABC right angled at B. Now this time, let the triangle be isosceles. Segment AB equals BC. Now in such a case, since angle A would be equal to angle C, my theta would become equal to 45 degrees. Now this time my base is equal to my perpendicular. Let us apply the Pythagoras theorem and we get P equals h by square root of 2. So my perpendicular and base being equal are equal to h divided by square root of 2. Now this time we are going to fill the column for 45 degrees. So let us write our trigonometric ratios in terms of P, B and H and substitute the values. We get sin theta and cos theta as 1 by square root of 2. Since the two are equal, tan theta becomes 1. And we can figure out the rest of the three ratios as reciprocals of the first three. Alright, now we are left with angles 30 degrees and 60 degrees. Now the easiest triangle with an angle of 60 degrees would be an equilateral triangle ABC, where AB equals BC equals CA. In other words, we could write angle A equals angle B equals angle C equal to 60 degrees. You can add up all the three angles and equate them to 180 degrees. Alright, now let us drop a perpendicular AD onto the side BC. Since it is an equilateral triangle, CD would be equal to BD. And AD would also act as the angle bisector. So my angle CAD would become 30 degrees. Now this time let us take theta equals 30 degrees. Now I can define my perpendicular as the side opposite to theta, my base as the side adjacent to theta, and the hypotenuse as the side opposite the right angle. Alright, now intuitively we can see that P equals h by 2, since BC would be equal to side AC. If you don't like the intuitive way, we can also prove the triangle ACD is congruent to triangle ABD. Let us see how. We can say that angle D is a right angle for both triangles. We can see that one of the angles is equal to 60 degrees since they belong to the bigger equilateral triangle. And we know that AC equals AB, once again due to the equilateral triangle ABC. Hence, we can see that from AAS property, the two triangles are congruent. Now, once again, I can say that angle CAD would be equal to 30 degrees, and let us call it theta. And now we can also confidently say that my perpendicular would be equal to half of the hypotenuse, since CD equals BD. Alright, so once again, applying the Pythagoras theorem, we get B equals square root of 3 by 2 times h. Now we know the values of B and P in terms of h. Now let us write our trigonometric ratios in the column for theta equals 30 degrees and substitute the values. We get very interesting values. We get sine theta as 1 by 2, cos theta as root 3 by 2, and we can figure out the rest of the ratios based on sine theta and cos theta. Now let us continue with the same triangle ACD, but let us call angle C as theta. So my theta is 60 degrees now. So my side AD would become the perpendicular and side CD would become the base. Once again, let us substitute the values for P, B and H in the trigonometric ratios for theta equals 60 degrees. Please note that sine 30 equals cos 60 and cos 30 equals sine 60. Or in other words, my sine and cos values for 30 degrees and 60 degrees are interchanged. This shall come handy later. Now how do I remember this complicated table? We only need to remember the sine and cos value for 0, 30 and 45 degrees. If we know these 6 values, we can easily fill up the rest of the table. Recall that sine and cos value for 60 degrees are interchanged with the values for 30 degrees. So, I can write 1 by 2 as cos 60 and root 3 by 2 as sine 60. We also noted that the sine and cos values are interchanged for 0 degrees and 90 degrees. So, I can easily write sine 90 as 1 and cos 90 as 0. And the rest of the trigonometric ratios can be derived from the values of sine theta and cos theta. Recall that tan theta is sine theta upon cos theta, cosec theta is 1 upon sine theta, sec theta is 1 upon cos theta, and cot theta is the reciprocal of tan theta. Let us look at a few problems. Evaluate 2 tan square 45 plus cos square 30 minus sine square 60. All the angles are in degrees. Now let us write our table for trigonometric ratios once again. We only need to remember the 6 values as shown. Now we are using tan 45 here. We can see that sine 45 equals cos 45. So tan 45 would be equal to 1. We also need the value of sine 60. Recall that we have to interchange the values of theta equals 30 degrees. Now we can easily pick the three values that we need to substitute here. And we get the value as 2. Let us look at another problem. In triangle ABC right angled at B, AB equals 5 cm and angle ACB equals 30 degrees. Determine the lengths of the sides BC and AC. Let us draw the triangle. Let us call angle ACB as theta, which is equal to 30 degrees. Now we can name the sides as P, B and H. If we write down the three basic trigonometric ratios that we know of, sin theta, cos theta and tan theta. Let us indicate the unknown values in bright red. So there is one unknown in sin theta, there are two unknowns in cos theta and there is one unknown in tan theta. You can pick any two of these ratios and figure out the sides BC and AC. Let us start with sin theta equals P by H. So we get sin 30 equals 5 by H. Now we know that sin 30 equals 1 by 2. Substituting, we get H equals 10 centimeters. Now since H is known, we can either pick the formula for cos theta or tan theta and figure out the value for B or the side BC. Let's take cos theta equals B by H and substitute the values. We get B equals 5 square root of 3 centimeters. Let us look at another problem. If tan A plus B equals root 3 and tan A minus B equals 1 by root 3, such that the value A plus B is more than 0 degrees and less than or equal to 90 degrees. Also, A is greater than B, then find A and B. Okay, let us go back to our table for trigonometric ratios and see if the values square root of 3 and 1 by square root of 3 appear anywhere. Now we know the 6 values, sin theta and cos theta for 0, 30 degrees and 45 degrees. Let us try to fill up the rest of the table based on these 6 values. We see that 1 by root 3 appears for tan 30 degrees. And we see that square root of 3 appears for tan 60 degrees. Now these are the two required values. Tan 60 is equal to root 3 and tan 30 is equal to 1 by root 3. But we are given that tan A plus B equals root 3 and tan A minus B equals 1 by root 3. Now since A plus B is less than 90 degrees, I can easily conclude that A plus B equals 60 degrees and A minus B equals 30 degrees. Adding these two equations, we get A equals 45 degrees. Substituting the value for A, we get B equals 15 degrees. Now this makes sense because A is greater than B.